this video, we are going to see how a dipole antenna can be simulated using CST. So here I am going to consider a wire type dipole antenna. These are some of the things that has to be considered before simulating a dipole antenna. We usually consider the length of the dipole as half wavelength, but due to the fringing effect means here you can see the electric field distribution in the dipole, and you can see the electric fields are extending beyond the dipole elements. And due to this extension or this fringing field, the effective length of the dipole will be seen as more than half wavelength. So while designing the half wave dipole, we have to take the length of the dipole antenna slightly less than the half wavelength. So here the equation is given as total length is 0.95 and multiplied by the half wavelength. This 0.95 depends upon the type of the material that we are going to use for the fabricating these type of antennas. And the radiation resistance of these dipole antennas are 73 ohm. So we have to use this factor for simulating this dipole antenna. And the directivity of the half wave dipole is 2.15 dB. So here I am going to simulate a dipole antenna at 2.45 gigahertz, and the wavelength at 2.45 is 122 mm. So based on this equation, the length is taken as 57.95 mm, and slight modifications on this length will be required because means effective length will be increased due to this fringing effect. So there may be slight modification on this length will be required. And the radius of the wire I have taken as 1 mm. If I take very thicker wires, it will effectively increase the length again, and the resonance frequency will be decreased. So here I am going to take the radius of wires as 1 mm, and the gap between the elements, as it is a wire type antennas, I am going to take the gap as 4 mm. So these are some of the things that you have to consider while doing this. Let's start. So I'm going to take the new template. As I'm going to consider a wire type antenna, I have to take that template based on that. So antennas, and then wire type antenna. I'm going for the time domain. As my frequency is 2.45, I'm going to take something in between 1 to 4, and next finish. So for the modeling, I have to take these wire type of dipoles, and I'm going to give the naming dipole. I have taken the radius as 1 mm, x center and y center as 0, 0, and z minimum and z maximum. That is our length. Length is 57.95. I'm going to take it as length as L, and the PC. So I'm going to take a preview. Length I'm going to give it as 57.95. Okay. So I have created this element. Maybe I will give the outer radius also as some parameters. Maybe later if you require some parameter optimization, we can use that value. So I'm going to create it. Now next we have to create a feed here. So for that I have to again create a cylinder. So I'm going to create that. So that is our feed gap. So for this also the radius has to be 1 mm, and maybe I have taken the gap as 4 mm. We have seen that. So I'm going to take G as 4. So I have created that. So my next step is I have to subtract that feed from the dipole. So I have subtracted. So now we have created the gap. So our next step is we have to like create a port in between these things. So what I have to do is I have to take the midpoint of this thing. So to take the midpoint of the face center, you have to click A, or you can select this option and click the midpoint. Or if you click A, you can select the midpoint of that face center. So I have clicked the A and taken the midpoint of these two face centers. So I have taken the face centers of two cylinders. Next thing is I have to assign a discrete port to that. So I am assigning a discrete port, and we have seen that the radiation resistance of dipole antenna is 73 ohm. So instead of 50 ohm, that is usually we take for all the microstrip antennas design. So here I have to take 73 ohm as the radiation resistance is 73 ohm, and just click OK. So I have created the discrete port here. So now our antenna is created, and we have to see what we have to see is we have to see the radiation pattern of the antenna and the current and electric field distributions of this antenna. So for that we can give the field monitors. I'm going to give the field monitor. Okay, maybe before that we can see what is the actual uh, resonant frequency of this antenna. So let's start the simulation. So my simulation is complete now. Let's check the result. So I'm going for 1D result, S parameter, S11, and I'm going to see what is my resonance frequency. Here you can see that the resonance frequency is 2.24. If you want to means optimize this resonance frequency, you can decrease this value, so you can effectively increase the resonance frequency. So here I am going to take this as the value, or if I need to optimize that, what I can do is I can give the parameter optimization. So let's see how we can do that. So for that you can go to the solver settings, and here you can see the parameter sweep, and what the parameter I have given L as the value for that our length. So I have to means optimize that value. So what I can do is I can click on new sequence, new parameter. As my parameter is L, I can do maybe up to 56 I can give. So based on your requirement, you can give more number of samples so that it will be divided from to two to that many number of samples. Here I have taken only 3 samples as it may take a lot of time to optimize this. So now I am clicking OK. Then if you click start, all the result for these three will be simulated. So I'm pausing my recording here, and I will restart once the simulations are complete. Okay, my simulation is complete. So here you can see that the results are obtained for different L length that we have defined. So let's see the values here. Here you can see for L length from 57.95 to 56 we have the values, and even though it is not yet optimized for 2.45, maybe if you want to optimize correctly to 2.45, maybe you can decrease the values again to 54 and do the simulations and take the values. For my purposes, I'm just going to take this value 56 as my value for the further simulations. So I'm going to take 56 for my simulations. So for that 56, the resonant frequency is 2.3. So now I have to create field monitors for the far field electric field. So let's do that. So I'm going to create the field monitors for 2.3, and I have created 2.3. Click apply, and next I have to create the far field also for 2.3. Click apply, and I have to also create the magnetic field or surface current, and click apply. So you can see you have created electric field, magnetic field and far field monitors. You can close this window and then you can just start the simulations. Okay, let's wait. So once the simulations are complete, it will be appearing in 2D, 3D results and the far field. So the simulation is complete. Let's check how the radiation pattern will look like. So means we know that the radiation pattern has to be look like a donut as it is inserted into this dipole. So here you can see that you have a donut shaped radiation pattern, and I'm going to just click show structure to show the structure, and I'm going to just decrease this one to see how it is like around the element. So here you can see that it looks like our donut is inserted into this element. So this is how the pattern will be looking like. So you can disable this show structure if you don't want to see the structure, but if you want to see how it is aligned with respect to the structure, you can use this value and you can use this scaling to see how it is. So this is the far field pattern. So if you want to see the cut plane result, you can go here and look for that. So if you want to see the plane along the x-axis, that is the figure of 8, you can see if you click phi equal to 0, you will get that cut plane. So phi equal to 0, if you click, you can see how it is aligned. That is, it looks like a figure of 8. And if you want to see another cut plane, you can click theta 90 degree, it will show the circular plane. So these are the two cut planes for the dipole antenna results. So the cut planes we have considered is along this plane and along this blue plane. So along this blue plane, that is theta equal to 90 degree, we have seen it will look like a circle. That is what we have seen here. So these are the 2D patterns. And now what we have to see is we have to see the current distribution and voltage distribution. So if you see the current distribution, you can see here that the current will be minimum at the ends and maximum at the center. For the voltage distribution, it will be reverse. As it is the open ends, the voltage will be maximum at the ends and minimum at the center. So let's see if we have seen like that in our simulation. So go for the electric field and click on that. So I have to see only on the cut plane. So I just click field on plane, cutting position x0. So I'm going to see contour. So here you can see for the electric field how it is. So we have seen for the electric field the maximum occurs at the ends. So if you want to see more accurately, you can scale this value by dragging, and you can see that the maximum electric field distribution is occurring at the ends. So if you see the current distribution, it will be reverse. If you want to see this using the arrows, you can also see using the arrows how the distributions will look like. And if you go for the surface current, here you can see that the current is maximum at the midpoints and minimum at the edges. So if you want to get a contour plot, you can select that and you will get a feeling that how the current distribution has happened here, the maximum at the midpoint and the minimum at the edges. So this is how the electric field and surface current distribution is simulated using the CST. So now you have seen how the dipole antenna can be simulated using the CST, and how the electric field, magnetic field and surface current distribution can be seen. So this is our 3D far field pattern, and if you want to see how the radiation from the dipole antenna happening, like these type of simulations, I'll be uploading the second part of the simulation to see how the radiation from the dipole can be seen. So this is this cut plane, y cut plane, where you can see how the field distribution from the dipole is happening, and along this cut plane, this is how the field distribution will be happening. So I will upload a second part of this video to show how this can be simulated. Thank you.